In every course that you take, there is a moment, generally, specifically in math. I don't want to speak for everything, but there is a moment where you realize that it does pay to do whatever it is that you were asked to do in the previous course. You know, like that moment in pre-calc when you shockingly remember the unit circle and it paid off on a particular question. Uh, in in Calc 1, it's just pretty much everything from pre-calc. This this could be one of those moments, but man, I'd give you a lot of credit if that were the case because we learn about natural law in this school. We learn about it at the end of college algebra with trig. It's not technically in the pre-calc curriculum. It sometimes, depending on the instructor, may be in Calc 1, but almost always is not. And then all of a sudden we're back to it in Calc 2 with the expectation that you know every aspect of it. Not recently, right? So in theory, you could be looking at least a year and a half between the last time you see something involving a log and when we actually implement these concepts in Calc 2. So we'll take baby steps when it comes to logs. I'll actually do more with that in Unit 2. So I don't want you to be terrified of Unit 2. It's not as bad as I'm making it seem. It's just this unit is the easy unit. All right, so every course has the easy unit. This is the easy unit. Unit 2, in comparison, will be much harder. That's not to say that it will be overly dreadful. So for now, recurring theme, put it in your calculator if you don't know what the hell a natural log function looks like. All right, hopefully you know what the line y equals 3 looks like, otherwise we should probably talk. We're looking for the area of the region bounded by y equals ln of x, the x and y axes, and y equals 3. So we're going to calculator. Take a look. Ln of x of y equals 3. Without getting into Zoom fit business, I think you can make some reasonable assumptions about what the window should look like. The x and y axes, so x min should be 0, y min should be 0. Y max, well, it's bounded by the natural log function and the line y equals 3. So it can't be much higher than 3. So maybe put in a 3, maybe put in a 4 to give yourself some wiggle room. If you're really concerned, put in a 5. The only value that is even remotely concerning would be the x max, because a natural log function is infinite, and it's a question of, well, when will this intersection happen? Is it going to happen early on? Is it going to happen later on down the line? If it happens later on down the line, when is that particular moment? That's where a little trial and error comes into play. But if you're doing trial and error with only one unknown constraint, that's not the end of the world. It's when you don't know the x min, max, y min, or y max at all, and you're just taking it from scratch. So I hit graph. That's when you have trouble. So it's telling me I got to go a little farther. So let's take a look. Maybe I'll try 20. Because I didn't get that intersection. I didn't get the intersection I was looking for. So window, let's try 20. I mean, you could also solve the equation, but I don't want to do that. Looks close enough, but I'd like to see a clear intersection. So I'm even going to go to 30. Or at least a reasonably clear intersection. Yeah, there we go. That's the ticket. I got some extra, I'm going to redo that snip. I got some extra fluff here that I don't want. A little bit better. Shrink it down. All right, so again, we decided 20 wasn't going to cut it. 30, maybe it was fine, but I didn't want to take the chance. So I went to 30. All right, so now I have a pretty good visual sense of what's going on here. But there's a little tiny tidbit of stuff going on here that maybe you don't necessarily account for, at least not without a little bit of experience with this stuff. All right, so the one thing you would not necessarily want to do is just subtract and go right to it. Let me show you a closer look at the calculator display. And in fact, I'm going to bring it back a lot. Right, so we have our intersection there. We know it's happening somewhere in the 20 to 30 region. All right, so we'll cross that bridge in a minute. So let me just focus in on this interval over here. Maybe only go out to like 5. Look at that. It's crazy. You have a little bit of sliver here of stuff, in which a little sliver of area in which the natural log plays no role whatsoever. This guy, this individual right here. I keep saying guy, but I don't think I'm allowed to anymore. It's 21st century. All right, so this area here is just a zoomed in version of that area. And that area doesn't contain a natural log at all. All that is an area bounded between the line y equals 3 and the x-axis. Find the area of the region, not write the sum of, or an integral over the sum of integrals to find the area. So I can actually look at this and say, well, this is a rectangle, base times height. I'm just counting boxes at this point, because again, I'm saying I'm not holding you responsible for logs and exponentials just yet, so everything related to that you can get off the calculator. So looking at this, you can see it's 1 tick mark over, base of 1, height of 3. Right, so off the bat, I know that I'm dealing with 3 plus something. That other something starts here and ends wherever here is. All right, so we have that whole other interval that we're looking for. All right, so okay, I was just making sure I didn't screw this problem up completely, because I was on a roll. We need this area here.
Function minus 3?
It's going to be 3 minus the function. Right. So we're going to look at dominant as the 3, non-dominant as the natural log for this interval. Right. If you want the area between them, that's how you're going to subtract. Right. So let me color code. I'm going to go blue for the non-dom. And I've already used green. I'll stay with the purple like this. So purple for the dominant. All right, so dominant function 3, y equals 3. Non-dominant, sorry, let me just clean that up. Non-dominant y equal ln of x. So we have antiderivative of 3 minus ln of x. Still don't have the interval yet, though. We're almost there. We'll have it in a second. I do know it starts at 1, though, if that matters for anything, because this rectangle here had a base of 1, and that corresponds with this distance, which means that where the first interval ended, the second one has to begin, making it a 1. So that part I got. It's the upper bound that I need, right? So I need that intersection. You can go decimal if you want. But we've done a little bit with exponentials and logs, at least converting back and forth. We haven't had to rely on all of the properties, etc. But if I want to find the intersection between two things, I just have to set them equal. So I'm going to say 3 equals, well, I'll say ln of x equals 3, so we have it in a convenient way of writing it. All right, ln, same as log base e. And we talked about nice circular motion as being my preferred way, anyway, of converting from logs to exponential form. So this would have it as e to the 3 equals x. All right, so that is actually the x value of the intersection. So this interval is going from 1 to e cubed. Now, e is 2.718 approximately. I just run that number for you real quick. E to the 3rd power is about 20-ish, a little bit more than 20. That's consistent with our diagram. If you didn't want to do it that way, that's fine. You can use the intersection function on your calculator. A lot of different purposes. If you did do that, then you just have to work with a decimal, but worse things about it. So this integral is going from 1 to e cubed. That little tail on the minus sign is bothering me. All right. We'll leave it at that for a second. We'll come to part B, and then the payoff for this problem will be when we check our answers against each other. Because if we change our perspective, we should still be looking at the same total area. So let us investigate. Oh, that was the zoomed in one. Dang it. Let me go back to, well, I guess now I can go, I know where the intersection is a little bit more than 20, so how about 21? All right, I mentioned 3 pages ago, that if you have an area that's entirely adjacent to a particular axis, that's the axis you want to be working with, right? So I have an area that's entirely adjacent to the y-axis. So I want to have an integral, or ideally I would integrate with respect to y. What that means, if it's entirely adjacent, it means that you can get the area with a single integral. Whereas if it's not, you have to use multiple integrals, multiple calculations in order to get what you're looking for. Or some sort of geometric sense, like that case with the rectangle with the 2 symmetric areas inside. If you know that it's the same and you can just come up with an integral that's equivalent, that's fine. But that's a rarity. In this case, we have an entire region that is bounded between a curve and the y-axis. So I want to integrate this with respect to y. Right? And here's the thing that people generally, in my experience, when they don't understand areas and volumes, they don't understand it because of this. So let me explain this, and please take it seriously. If I'm looking for a distance from an axis, going right back to middle school, I can be going from the x-axis or from the y-axis. All right. A horizontal distance, a distance from the x-axis, is some, I'm sorry, distance from the y-axis is some distance x. It's x units away, right? If I plotted a point like, I don't know, I'll keep it very simple, 2, 1. This point is 2 units away from the y-axis, 1 unit away from the x-axis. You don't tend to think of it that way, though, because, and it's really having to do more so with how you learn to plot points to begin with. You traveled along the x-axis, and then you traveled up or down. And that kind of leads to misconceptions. The idea is that your x value is always your distance from the y-axis. Your y value is always your distance from the x-axis. Right? So when I'm looking for the appropriate expression to write in here for my integral, I'm looking for 2 things. One, I'm looking for the orientation of an arbitrary rectangle that would exist within the curve, and that's where the tech assignment is going to come into play. That arbitrary rectangle has a thickness related to y. It has a very tiny change in y. That's where the dy is coming from. It's an infinitesimal change in y, almost non-existent. But that's where the concept of an instantaneous rate of change, things like that, comes from. Right? Corresponding with that, I have a horizontal distance, which is a distance from the x-axis. From the y, I keep saying that, from the y-axis, known as x. That x should be a function of y. It should be x of y. dy. We say the antiderivative with respect to y, just as a really short way of saying what I'm trying to say here, is that my perspective is from the orientation related to the y-axis. Right? So when I'm actually saying with respect to y, I'm saying that I am standing on the y-axis, and that is my perspective. I'm looking out from the y-axis. Right? So that's what we're talking about with respect. It's not, a compliment to anyone. It's saying what your vantage point is. If I say it's with respect to x, I'm standing at the x-axis, and I'm either looking up or down. It's perspective. So once you identify your perspective, you have to figure out the other dimension. The reason why I need an x value is because it creates the rectangle. Rectangle has an area of base times height. Whatever one's base, whatever one's height. X times dy. So that gives me a single area of a single rectangle. If I integrate, I'm going to get every possible rectangle from the beginning of my interval to the end of my interval. That's what the integral does to this. This gets us a single rectangle on the interval. This gets us all of them. It's a sum of every one of them together.
That's right, going back to the nation class, that's the net area.
That's the net area on the interval. All right, so very important, can't emphasize it enough. All right. Once you change your perspective so that you're looking in terms of y, everything goes in terms of y. So bounds, in this case, much easier to find the bounds, right? 0 to 3. That was all just given. The only challenge that remains is coming up with a function of x in terms of y related to this curve. So this curve was y equals the natural log of x. But I want to write it as x equals. What does x equal? E to the y. All right, and that's the rationale behind that is the same as the rationale over here. Instead of ln of x equals 3, I would say ln of x equals y. E to the y equals x. All right. So now I have a function solved for x in terms of y. Still don't have to do it by hand, but if I did, I would much rather work with this expression than this one. All right. The idea here is to recognize that you can go from the perspective of X and or the perspective of Y. In some cases, in the cases of area, it leads to convenience. One way is nicer than the other. But we're getting into topics starting next class where it's not convenience, it's necessity. All right? So, and just for the payoff. Alpha, window 4. I'll do this one first. You can put Y's in if you want, if it really makes you feel warm and fuzzy. Second, ln, and then, yeah, just to satisfy that need. You can put an X in too, doesn't make a difference, as long as the variables are consistent. Get that. Just making sure I typed it in the right way. And then the other guy, 3 plus, or gal, alpha window 4, 1 to, you see I'm already tired of typing it in this way. I don't want to do it this way. But we do it. And there it is. To put it back in terms of E? Oh, because it's clean. Yeah, if you do it by hand with this, it's clean. Oh, I would just say give me a rounded number, but let me just think for a sec. Yeah, I think it's the +3 that's going to screw it all up. I mean, if you go the anti-log route, it would get you there eventually, but I have to think about that. What did I say, 19.9? 19. Approximately 19. All right, so let me put a star on this puppy. Yeah, the next class is volumes. The key to understanding volumes is understanding areas.